Imagine a battery that doesn't run on chemicals or stored sunlight, but draws energy directly from the empty space between two plates. It sounds like something out of a mid-century science fiction novel, yet in 1984, a physicist named Robert L. Forward published a paper in Physical Review B titled Extracting Electrical Energy from the Vacuum by Cohesion of Charged Foliated Conductors. He wasn't talking about magic, he was talking about the Casimir effect, a phenomenon where the vacuum of space exerts a physical force on objects. If we can harness that force, we might be looking at a completely different way of thinking about energy storage and extraction.
The foundation of this whole idea is that the vacuum isn't actually empty. In classical physics, a vacuum is just void, but in quantum mechanics, it is teeming with activity. There are these things called zero-point fluctuations, basically electromagnetic waves that exist even at absolute zero temperature when all other energy has been removed. In 1948, Hendrik Casimir predicted that if you place two uncharged conducting plates very close together in a vacuum, these fluctuations would create a pressure that pushes the plates together. This isn't a speculative force. It has been experimentally verified multiple times, most notably by researchers like Steve Lamore in the 1990s, and even earlier experiments mentioned by Forward using mica cylinders.
It's a bit counterintuitive to think of nothing having a pressure. How does a lack of particles result in a physical squeeze on metal plates? Usually when we think of pressure, we think of air molecules bouncing off a surface. But here, the vacuum itself is the actor. Why does it only happen when the plates are incredibly close together?
Think of it like waves in a harbor. Outside the harbor, you have waves of all possible lengths. But inside the harbor, between two docks, only certain wave sizes can fit comfortably without crashing into the walls. In the vacuum between two conducting plates, the electromagnetic fluctuations are restricted. Only certain wavelengths can exist in that narrow gap. Meanwhile, outside the plates, there's a literal infinite variety of wavelengths pushing inward. This creates a disparity in radiation pressure. The outside pushes harder than the inside, and the plates are forced together. Forward's paper notes that this force becomes significant at distances less than 1 micrometer and gets exponentially stronger as the plates get closer.
So the vacuum is doing work. It's moving the plates. Forward's big leap was suggesting we could turn this mechanical movement into electricity. He describes a vacuum fluctuation battery. But if the Casimir force is purely attractive, wouldn't the plates just snap together and stay there? How do you get a continuous cycle out of something that seems to want to reach a state of permanent cohesion?
That's where his foliated conductor design comes in. He envisions a stack of ultra-thin aluminum foils, like the leaves of a book, but separated by microscopic distances. To prevent them from just sticking together instantly, he proposes charging each plate with the same polarity. Since like charges repel, you have this repulsive electrostatic force fighting against the Casimir force. If you use a sophisticated electronic control system to keep the electrostatic repulsion just slightly weaker than the Casimir attraction, the plates will slowly move toward each other. As they move, the Casimir force is doing work against that electric field, essentially pushing energy into the circuit.
It sounds like a delicate balancing act. If the electrostatic force is too weak, they crash. If it's too strong, they move apart. But Forward claims this is a way to extract energy from the vacuum fluctuations. This brings up a major question regarding the laws of thermodynamics. If we are pulling energy out of the vacuum, are we getting something for nothing? Is this a perpetual motion machine in disguise?
Forward is very careful about this in the paper. He acknowledges that there's no rigorous proof that the vacuum fluctuation field is conservative, like gravity, but he assumes it is. If it's a conservative field, you aren't creating energy out of thin air in a way that violates the first law of thermodynamics. He uses the analogy of a hydroelectric dam. The dam doesn't create gravity, it uses the gravitational potential of water. The water was put in that high potential state by the sun evaporating it from the ocean. Similarly, a foliated conductor, a stack of separated foils, is in a high potential energy state because of its large surface area and separation. When the plates cohere into a solid block, they move to a low potential state. You are essentially mining the potential energy that was already there when the foils were manufactured and separated.
So the energy isn't really coming from the void in a way that lasts forever. It's more like the Casimir force is the mechanism that lets us tap into the energy stored in the physical structure of the foils. But wait, if we have to use energy to manufacture the foils and separate them, and we use energy to charge them and run the sensors for the feedback loop, does the math actually work out? Do we get more out than we put in?
That is the million-dollar question. Forward's paper is a conceptual proposal, not a blueprint for a commercial product. The energy density he's talking about is quite small at micrometer scales, but becomes massive at the nanometer scale. He points out that experimental data from 1972 using mica cylinders showed forces over 10 kilonewtons per square meter at a separation of 1.4 nanometers. That's a huge amount of pressure for a microscopic gap. However, the engineering challenges are immense. To make this work, the surfaces have to be perfectly flat at an atomic level. If there are any bumps, or surface roughness as Forward calls it, the plates will touch at one point and the whole system shorts out or sticks before you can extract meaningful energy.
He mentions molecular beam epitaxy or atomic spray guns as a potential solution for making these perfectly flat plates. That was cutting edge in 1984. Today we have much better nanotechnology, yet we don't see vacuum fluctuation batteries in our phones. Is the issue just that the amount of energy is too small for the cost of the hardware, or is there a deeper physical limitation?
It's likely a combination of both. Even if the physics holds up, the active bidirectional power supply needed to stabilize the plates would be incredibly complex. Remember, this system is inherently unstable. It's like trying to balance a needle on its tip while a magnet is pulling it down. The sensors and the feedback loop might consume more energy than the Casimir force provides. Furthermore, while the paper suggests you can recharge the battery by pushing the plates apart with a stronger electrostatic force, that would require an external energy source. So in that mode, it's just a storage device, a very high-tech capacitor, rather than a primary energy source.
But if we look at it as a primary source, the fuel is the cohesion of the plates. Once they turn into a solid block of aluminum, the battery is dead. You'd have to physically manufacture a new foliated conductor to get more energy. It's almost like a very high-tech version of a spring that's already wound up. You're just letting it unwind. Why would Forward frame this as extracting energy from the vacuum if the energy is actually coming from the potential energy of the foil's arrangement?
Because the vacuum fluctuations are what facilitate that unwinding. Without the Casimir effect, those plates wouldn't feel that specific pull. In his view, the vacuum is a catalyst. It's a subtle distinction. Think of it like a siphon. The gravity pulls the water through the tube, but the siphon is the tool that makes the energy transfer possible. He's suggesting that the vacuum is a reservoir of energy that we can interact with if we build the right mechanical interface at the nanoscale. He even proposed a slinky, or spiral design, to make it easier to fabricate, where one long continuous strip of foil is coiled so that each layer acts on the next. This would simplify the electrical contacts significantly.
There's a certain irony in using electrostatic repulsion to control a quantum vacuum force. We are using one of the most well-understood forces of the 19th century to manage one of the most mysterious forces of the 20th. Did Forward address the controversy surrounding the zero-point energy? There's a lot of debate in physics about the vacuum catastrophe. The fact that our calculations for how much energy is in the vacuum are off by about 120 orders of magnitude compared to what we actually observe in the expansion of the universe.
He doesn't dive into the cosmological constant problem, but he does touch on the Lifshitz theory, which expanded Casimir's work to include dielectrics, non-conducting materials. This is important because it shows the force is universal. It doesn't matter if it's aluminum or mica or silicon. If it's a boundary in space, it's going to interact with these fluctuations. The controversy in Forward's time was more about whether this force could ever be practical. Most physicists at the time saw the Casimir effect as a laboratory curiosity, something that made it hard to build tiny machines because the parts would stick together, a phenomenon known as stiction in MEMS, or micro-electromechanical system.
So what everyone else saw as a nuisance, this stiction that ruins micromachinery, Forward saw as a power source. He wanted to lean into the stickiness of the universe. It's a brilliant bit of lateral thinking. But let's talk about the cultural impact of this paper. It was published in Physical Review B, a very serious peer-reviewed journal. How was it received? Did people try to build it?
It was received with a mix of fascination and skepticism. Robert Forward wasn't a crackpot. He was a well-respected physicist at Hughes Research Laboratories and worked on gravity wave detectors. Because of his credentials, the paper wasn't dismissed. However, the sheer difficulty of creating a stack of thousands of plates, each a nanometer apart, and controlling them with a sub-nanosecond feedback loop meant that it remained a thought experiment for decades. It did, however, inspire a lot of interest in zero-point energy in popular culture, though often in ways that misinterpreted Forward's careful physics. You'll see his work cited in everything from free energy websites to hard sci-fi novels like those by Stephen Baxter.
And that's the danger, isn't it? When a legitimate scientist talks about extracting energy from the vacuum, it becomes a rallying cry for people who think we can solve all our energy problems with a magic box. Forward is very specific. You are extracting energy from the cohesion of the conductors. Once they are coherent, once they are a solid block, the extraction stops. It's not an infinite fountain.
Exactly. It's finite. The total energy you can extract is essentially the difference between the surface energy of all those individual foils and the surface energy of a single solid block. That's a lot of energy at the nanoscale, but it's still limited by the mass of the material you have. It's like a chemical battery where the chemicals are the physical shapes of the metal itself. In 1984, Forward was trying to push the boundaries of what we considered fuel. He was saying that geometry can be fuel.
That's a powerful idea. Geometry as fuel. If we look at recent developments like researchers using the Casimir force to drive the motion of tiny silicon gears, we're seeing a version of Forward's dream coming true, even if it's not a battery in the traditional sense. We are using the vacuum to do mechanical work at the micro scale. What's the biggest takeaway here? Is it that the vacuum is a resource, or that our understanding of empty is fundamentally flawed?
The takeaway is that the boundaries between material and space are much blurrier than they appear. The Casimir effect shows that matter is constantly interacting with a sea of background energy that we usually ignore. Forward's vacuum fluctuation battery might never be a practical way to power a car, but it forces us to acknowledge that the vacuum is a physical substance with properties we can manipulate. It challenges the 19th century view of energy and pushes us toward a future where we might manipulate the very fabric of space to perform small-scale work.
It's a reminder that sometimes the most revolutionary ideas come from looking at a known problem, like micro parts sticking together, and asking, what if this isn't a bug but a feature? Robert Forward took a quantum mechanical headache and tried to turn it into a power plant. Even if the engineering isn't there yet, the conceptual leap remains one of the most fascinating intersections of quantum field theory and electrical engineering.
Imagine a space that is completely empty. No air, no light, no stray atoms, just a perfect vacuum. In classical physics, this nothingness stays nothing. It exerts no pressure and holds no energy. But quantum mechanics suggests a far more chaotic reality. In that silence, there is a constant, invisible storm of energy. This isn't just a theoretical curiosity. It's a force that physical objects feel. It pulls them together with enough strength to wreck the microscopic machines that run modern technology. This phenomenon is known as the Casimir effect. It represents one of the most direct proofs that the vacuum isn't empty, but rather a sea of fluctuating fields. While some people dream about it as a source of limitless energy, working on microchips see it as a fundamental enemy. It's the primary cause of stiction, a unique type of microscopic friction that causes tiny components to glue themselves together permanently. To understand why your smartphone sensors work or why future nanotechnology faces a massive hurdle, we have to look at how the universe tries to stick itself together at the smallest scales.
That description captures the tension perfectly. The Casimir effect emerges from the Heisenberg uncertainty principle. This principle dictates that energy and time have a relationship where you can't have a zero energy state for any duration of time. Even in a vacuum, fields like the electromagnetic field are constantly fluctuating. These are often called virtual particles. They pop into existence and disappear almost instantly. In open space, these fluctuations happen at every possible wavelength. They push in every direction equally, so we don't feel them. However, in 1948, a Dutch physicist named Hendrik Casimir realized that if you place two uncharged conducting plates very close to each other, you change the environment for those fluctuations. Only certain wavelengths can fit between the plates. Long wavelengths are excluded. Outside the plates, every wavelength is still present. This creates an imbalance. There's more pressure on the outside pushing in than there is on the inside pushing out. The result is a measurable, attractive force that pulls the plates together.
The idea that the vacuum exerts pressure sounds like something out of a science fiction novel, but it took decades to prove this with any real precision. If the force is so fundamental, why did it take until the late 20th century for scientists to verify it? If the vacuum is pushing on everything, shouldn't we see things moving around all the time? It seems like this force is selective, or perhaps just so weak that it only matters in very specific laboratory conditions.
The force is weak in our everyday world because it scales with the inverse fourth power of the distance between the objects. If you double the distance, the force drops by a factor of 16. For objects separated by a millimeter, the force is non-existent for all practical purposes. It only becomes significant when the gap is measured in nanometers. Hendrik Casimir was working at Philips Research Laboratories when he proposed this. He was actually studying colloidal suspensions like paint or ink, trying to understand why they were stable or unstable. He noticed that the existing theories of van der Waals forces didn't quite match the experimental data. Along with Dirk Polder, he developed the theory that the finite speed of light limits these interactions, leading to what we now call the Casimir-Polder force. But the first high-precision measurement didn't happen until 1997. Steve Lamoureux at Los Alamos National Laboratory used a torsion pendulum and a gold-coated sphere and plate. He managed to measure the force to within 5% of the predicted value. A year later, Umar Mohideen at the University of California, Riverside used an atomic force microscope to confirm it with even greater accuracy. These experiments proved that the vacuum energy is real and its effects are predictable.
So we have this force that essentially pulls objects together, because the vacuum between them is less crowded than the vacuum outside. That's a fascinating bit of physics, but the claim is that this is a nightmare for engineers. We live in an era of microelectromechanical systems, or MEMS. These are the tiny accelerometers in our phones that detect orientation, the mirrors and digital projectors, and the sensors in car airbags. At the scale these devices operate, components are separated by tiny gaps. Does the Casimir effect become the dominant force there? Is it enough to actually stop a machine from moving?
It is a massive hurdle. In the world of MEMS, surfaces are so close together that the Casimir force, combined with van der Waals forces, creates a phenomenon called stiction. Stiction is a portmanteau of static friction and adhesion. When a tiny cantilever or a gear in a MEMS device gets too close to another surface, these quantum forces snap them together. Once they touch, the contact area is so large relative to the mass of the parts that they become permanently fused. It's like trying to pull apart two pieces of wet glass. The force required to separate them is often greater than the strength of the material itself. This isn't just a minor annoyance. It is a primary failure mode in the manufacturing of micro devices. If the humidity is too high or the design has too much surface area, the yield of functional chips drops. Engineers aren't just fighting gravity or traditional friction, they are fighting the fundamental nature of the vacuum.
It seems ironic that as we try to make technology more efficient by shrinking it, the laws of physics themselves begin to act as a glue. If the Casimir effect is a result of geometry and vacuum fluctuations, it doesn't seem like something you can just switch off. Gravity always pulls, and the vacuum always fluctuates. How do you design a machine that functions when the very space it occupies is trying to collapse its parts together? Are there materials or shapes that can bypass this? Or is there a hard limit to how small we can go?
Engineers have developed several strategies to fight back. One common approach is to change the surface chemistry. They use self-assembled monolayers, which are thin coatings of molecules that act like a microscopic layer of Teflon. These coatings reduce the surface energy and make it harder for parts to stick. Another method involves physical texture. If you look at a MEMS component under an electron microscope, you might see tiny pillars or bumps called dimples. These serve to minimize the contact area. By reducing the area where the surfaces are close, you reduce the total Casimir force. But the most exotic solution involves manipulating the force itself. In 2009, a team at Harvard University, led by Federico Capasso, demonstrated that the Casimir force can be made repulsive. By choosing specific materials and immersing them in a liquid, they changed the way the fluctuations interacted with the surfaces. They used a gold-coated sphere and a silica plate submerged in bromobenzene. Because the dielectric properties of the liquid were between those of the two solids, the vacuum pressure pushed the objects apart instead of pulling them together. This opened the door to frictionless bearings and levitating components at the nanoscale.
The idea of a repulsive Casimir force suggests that we could have components that never touch, essentially floating on a cushion of quantum fluctuations. That sounds like a solution to the stiction problem, but it also sounds complex to implement in a consumer device like a smartphone. You can't just fill every microchip with bromobenzene. If the goal is to create reliable nanotechnology, we have to find ways to manage these forces in ambient conditions. I wonder if the focus on fighting the force misses a larger point. If the Casimir effect is a source of pressure, why is the conversation always about it being a nuisance? There is a lot of talk online about zero-point energy and using the Casimir effect as a power source. Is there any truth to the idea that we could extract work from the vacuum?
That's a point of significant contention. In theory, you could extract work once. As the plates move together, the Casimir force does work on them. You could capture that energy. However, once the plates are stuck together, the process is over. To get more energy, you would have to pull the plates apart, which requires more energy than you gained because you're fighting the same force that pulled them together. It's a classic thermodynamic trap. The vacuum energy is the lowest energy state of the universe. You can't consistently extract energy from the lowest state without a lower state to dump it into. Most physicists agree that the free energy claims regarding the Casimir effect violate the second law of thermodynamics. While the force is real and powerful, it's more like a compressed spring that you can only release once. The real value isn't in power generation, but in precision control. If we can manipulate these forces, we can build sensors that are far more sensitive than anything we have today. For example, LIGO, the observatory that detects gravitational waves, has to account for quantum noise that is related to these same vacuum fluctuations. Understanding the Casimir effect is about mastering the environment at the most fundamental level.
So instead of a battery, it's more of a limit on how we build. If we look at the cultural legacy of this discovery, it shifted how we view the void. Before Casimir, the vacuum was just a stage where things happened. Now it's an active participant. This brings up questions about the nature of space-time itself. If the vacuum has this much power at the nanometer scale, does it have implications for cosmology? Does the Casimir effect relate to the broader history of dark energy, which is also described as a property of space that exerts pressure?
There is a deep and frustrating connection there. Physicists have tried to use the math of the Casimir effect to calculate the energy density of the universe. This is known as the cosmological constant problem. When you use quantum field theory to calculate how much energy should be in the vacuum, the number you get is about 120 orders of magnitude larger than what we actually observe through astronomical measurements of the expansion of the universe. This is often called the worst prediction in the history of physics. We know the Casimir effect is real because we can measure it in the lab with MEMS intorsion pendulums. We know the vacuum energy must exist, but we don't understand why the entire universe hasn't been blown apart by it or collapsed under its weight. The Casimir effect is the small-scale proof of a mystery that spans the entire cosmos. It shows us that our current understanding of how gravity and quantum mechanics interact is incomplete. Every time a MEMS engineer tries to keep a tiny switch from sticking, they are touching a piece of that massive, unsolved puzzle.
It's a striking thought. A failure in a microscopic sensor is essentially a localized symptom of our incomplete understanding of the universe. We've talked about the engineering solutions, like coatings and repulsive forces, but there is also a debate about the role of the materials themselves. Different materials have different plasma frequencies, which affects how they reflect those virtual particles. Does this mean the future of micromanufacturing is less about mechanical design and more about advanced material science? Perhaps choosing the right alloy or crystal structure is the only way to coexist with these quantum forces?
Material science is definitely the frontier. Research is moving toward metamaterials, engineered structures that have properties not found in nature. By designing materials with specific optical properties at the scale of wavelengths, we can potentially tune the Casimir force.
Scientists like Leonhardt and Philbin have researched how transformation optics can be used to mask or even reverse these forces. There's also work into using graphene. Because graphene is a two-dimensional material with unique electronic properties, its Casimir interaction is different from bulk metals. It allows for a higher degree of transparency to certain fluctuations. This could lead to devices where parts can move past each other without the risk of snapping together. The challenge is that these materials are difficult to produce at scale. Right now, the industry mostly relies on more pragmatic fixes, like the dimples and hydrophobic coatings I mentioned earlier. But as we move toward the next generation of nanotechnology, these brute force engineering methods might not be enough. We will have to start designing for the quantum vacuum from the ground up.
This really changes the perspective on what miniaturization means. It's not just making things smaller, it's moving into a regime where the forces we take for granted, like gravity, disappear, and forces we never think about, like the Casimir effect, become the masters of the house. It's a world where nothing is actually a sticky, pressurized medium. The fact that we have functional micromachines at all is a testament to how well engineers have learned to navigate this invisible minefield. Even though it's not the infinite power source some hoped for, it's a fundamental reality that defines the limits of human fabrication.
That's exactly right. The Casimir effect is a reminder that there is no such thing as a passive environment. Space itself has texture and weight when you look closely enough. We often think of technology as something we impose on the world, but at the nanoscale, technology is a negotiation with the vacuum. Whether it's through the discovery of repulsive forces or the development of non-stick coatings, we are learning to live in a universe that is, by its very nature, incredibly sticky. This research doesn't just stop stiction in our sensors, it pushes us toward a more unified theory of physics. It bridges the gap between the mundane reality of a sticking gear and the grand mystery of the expansion of the universe. It's one of those rare areas where a very practical engineering problem is directly linked to the deepest questions of existence.
It seems clear that the Casimir effect is much more than a laboratory curiosity. It is a defining factor in the success or failure of the technology that fits in our pockets. From the early predictions in 1948 to the high-stakes engineering of modern MEMS, we have come to see the vacuum as a dynamic, forceful presence. While we might not be harvesting it for electricity, we are certainly learning to dance with its fluctuations. By understanding stiction and the quantum forces behind it, we are building a foundation for a future where we can manipulate matter at its most fundamental level.